So there are types of equations that you guys don't know about yet, okay? And we will learn when we get to those. There'll be a different way of solving them than what we solved already, okay? That being said, there are different types of inequalities down the road towards the end of the textbook and the other math courses that you will be introduced to and how to solve those. So what we go through here is only going to solve a special set of inequalities, and it's not all types of inequalities. Does that make sense? Okay. When we're introduced to the next types of equations towards the middle to end of this textbook, the next thing we'll do after we learn those equations, we will then look at how we solve inequalities that look just like it. Okay. So that's kind of the idea. As you go through the next 2, 3, 4 years, as you learn to solve a particular type of equation, the next thing you learn is to solve the inequality that looks like that equation. Okay. So I guess what I want to say here, and I don't want you to mislead you, is that this is not the way to solve every single inequality you ever come across. This is only going to work with when you have a variable x and the exponent is a 1 with it. If the exponent is 2 or 3 or 4, there's a different approach. Okay. So when solving inequalities, we solve them just like equations. Nothing really different. There's one thing that's different. We'll get to that tomorrow. That's what it says in parentheses there. It's when you divide or multiply to solve for x. There's a special situation that occurs. It doesn't always occur, but we have to be on the lookout for it. But other than that, you solve them just like any other equation you've ever come across. Okay. What allows us to do that is our understanding of our addition properties, subtraction properties, division properties, that kind of thing. And this is hopefully going to kind of explain that. If I look at this statement, if 3 is greater than -1, 3 is greater than -1. So I'm going to look at a picture here. Here's 3. Let's go to -1. Okay. Do you agree that the red dot is further to the right than the blue one, right? That makes that statement, we understand that statement to be true. Okay. Well, what do I get if I add 2 to both sides of that? Okay. If I add 2 to that 3, what do I get? 5. We'll plot that there as an X. Okay. So the red dot went to the red X. What do I get if I add 2 to -1? +1, right? Okay. Is the red X still bigger than the blue X? Can that make sense to everybody? So when I take -1, and I add to it 2, and it moves to right there. But when I take +3 and add 2 to it, and it moves it right there, that is still bigger than that. Okay? And that's the addition property of inequalities that allows us, when we're solving an inequality, to be able to add the same thing to both sides, or ultimately subtract the same thing from both sides. Okay. Down here, this is a generic statement that says if A is greater than B, let's just put maybe let's put B right there. Come over here and put A. Would you agree that in that number line, A is bigger than B? A is further to the right, correct? Okay. Now it says what happens when you add C to both sides? Well, if I add C, so right here, if I'm starting at B, I want to add C, it would get me to that spot right there, right? I'll call that B plus C. If I did that to B, let's add that to A. And so give me this spot right here. We call that A plus C. But is the argument still the same, that that thing right there is still further to the right than that thing? That makes sense, everybody? So what the argument then is, well, if I start with A greater than B, then A plus C is still bigger than B plus C. Adding the same thing, to both sides, maintains the same inequality. Okay? That makes sense? That's what allows us to solve inequalities the exact same way as the way we solve equations. Okay? Now, when we solve equations, we do subtraction. Well, subtraction is adding the opposite. So we would just move to the left on both those instead of moving to the right. eventually when we start dividing and multiplying to isolate variables and that kind of thing, the concept is really the same thing that's going on right there. Okay, but instead of addition, it'd be multiplication division. So we get some examples. Okay, using that approach, if I have the inequality x minus 15, x minus 15 is greater than negative 12, and I want to solve that. I solve it just like solving any other equation. You want to isolate your variable term, right? We want to get that x all by itself. Okay? This thing here, that symbol, is what creates a left side and a right side of my inequality, correct? So I was kind of taking the place of the equal sign in the equation. So if I want to get this x all by itself, what is on that side with x? 15. How do I get that 15 to go to 0, to disappear essentially? Add 15. It's the exact same thing you would have done if this was an equal sign, right? Add 15 to the left, what do I do to the right? Add 15. Okay? So it gives me x. Now this symbol stays that, call that a greater than symbol in this case, remembering left to right. Then negative 12 plus 15 is 3, right? So saying x is greater than 3. We come to our picture, or our graph. We've got x is greater than 3. I go find 3 on my number line. What kind of dot do I use? An open one or a closed one? Open, good. So that was what we talked about yesterday, right? This is the part where once we get our answer, we have to rely on what we learned in 3.1. Okay, so open dot. Now, which way do I shade? Or which way do I point my arrow, left or right? To the right. Okay, these are the numbers that are greater than 3, right? Okay. I don't know if I said this to you guys or we realized this yesterday or not. When you write your variable first in your expression here, or your inequality, x is greater than 3. I've been using kind of the analogy that inequality symbol kind of points as an arrow to a smaller number, right? Okay. If you write your variable first, that symbol also kind of points to the direction that you need to draw your arrow in your graph. Does that make sense? Is that pointing to the right? Did we shade to the right or graph to the right? When I say graph or shade, I mean which way I drew my arrow, right? Did I do that to the right? Yeah. But that only works. And that will always work as long as your variable is written first in your part that I highlighted there, the x is greater than 3 statement. Okay. Now, what does that mean? That means I've got an infinite number of answers. That means any number that I choose that is over here, when I plug in for that x, so what will be a number that's over here? Give me any number that is bigger than 3. Okay, 5. So I should be able to go 5 minus 15. That should be bigger than negative 12. Is negative 10 bigger than negative 12? Yeah. Okay. What if I choose, this goes up to 6, but is like 600 on here? Yeah, if I go 600 minus 15, is that bigger than negative 12? Yeah, 585 is bigger than negative 12. Okay? That's what that's referring to. That all those solutions that are being graphed there in orange or blue, whatever color we're going to refer to there, there's an infinite number of them. And when I plug them in, they're going to give me a true statement in the inequality. Okay. If we come down to the next one, okay, what are you going to do first there? And the 10 is greater than or equal to, 10 is greater than or equal to x minus 3. Add 3 to both sides. So we're trying to isolate our variable. Add 3 to both sides. It's going to be 13 is greater than or equal to x, right? Now, I hate that structure of that solution. I like to write it as x first, 13 second. With that symbol right there, and this statement is pointing towards the x, right? So when I flip these around, it needs to point to the x. That's not an issue with an equal sign because an equal sign is the same way, either way, left to right, as you read it. With an inequality, you have to pay attention to that idea. Okay? So now x is less than or equals 13. Well, I go find 13 on my number line. So, you guys agree 13 is probably about right here? Okay? Got to make the right kind of dot, open or close. Should be closed because of that equality, right? Okay? And then the arrow's pointing. If that's an arrow, it's pointing to the left, right? So all these numbers are the ones that are less than 13. We talked about the other day, I don't know if I said this in both classes, when we have less than or greater than, that gives us an open dot. And if we have less than or equal to or greater than or equal to, that gives us a closed dot. Did I give you a reason or a way of remembering which one was which? If I look at these two things, which ones, the top ones or the bottom ones, took more ink to draw? The bottom one took more ink, right? When you look at these two, which one took more ink to draw? The bottom one, right? So the inequality symbols that require more ink are going to be then connected to the dot that requires more ink. Does that make sense? I would, when I was your age, I would dot things like that, because there's a lot of stuff in mathematics that are like this, where we take a symbol and we change it to kind of a notation of a dot or a closed dot or something like that, where we lose sometimes meaning, and it's hard to kind of connect things that way. I always try to make kind of like weird, to other people might seem weird connections that allow relations, allow me to remember things. I think that one's useful. Okay, if you can do those types of things, so that makes sense to you, please do those. And if you come up with anything that makes sense to you like that, let me know. Maybe it's something that I could use and share with other people to help them remember things. Okay, instead of trying to, I guess, memorize, I've tried to build those relationships and do things that way. There's an assignment in Math Excel. What I'm going to start doing, guys, is with your Math Excel assignments, I'm going to cut down the amount of new questions I put in them. Okay, so today I wanted to give you 20 questions over this stuff. What I did is I cut it to 15, and then I sprinkled in 5 questions from stuff that we've already done. Okay, so that stuff is always kind of constantly being used and looked at. Okay, because when you get to the end of course exam, it's going to be something over the entire year, right? Well, I don't want you to be just focused on what we just did in Chapter 12. I want us that in an assignment in Chapter 12, there could be questions from Chapter 2, 4, 7, okay? And I just want to keep that stuff fresh, okay? So that's kind of what we're going to do as we continue to move on. So there still is 20 questions, but only 15 come from this assignment. So tomorrow, maybe 3 or 4 will come from today, 3 or 4 from Monday. Does that kind of make sense? Overall, you're not going to miss out on, you're going to say, well, I could have used the 20 questions out of this section. You'll see them. You'll just won't see them today. You'll see part of them tomorrow. Okay? So that's just kind of, you might be doing your homework and say, well, this is weird. We've already done this. And that's intentional. I'm doing that on purpose. That's all I've got for you. I don't know what time we get out of here. You guys know? 07? Okay. So you've got, 15 minutes here. Not 15, 12 minutes. 13 minutes. You can work on that assignment. Okay. And the last class obviously had a little bit more time than you, but they got it done pretty quickly. So you can get a pretty big dent in that assignment.
Can I use the